Hello and welcome to the course Sequence Modeling Part 2. In this course, we are going to discuss Gated Recurrent Unit, popularly known as GRU. Then we will discuss the GRU architecture. Then we introduce sequence to sequence modeling and how attention is used for this sequence to sequence modeling. Then we learn how to compute attention through RNN. Okay. So, in this gated recurrent unit, it's more popularly known as GRU. It is basically a simpler alternative to LSTM, what we have discussed earlier. So it has been proposed by Cho et al. At 2014. Now it is also a RNN, but with some similar kind of architecture designed to handle the sequential data and solve the vanishing gradient problem found in traditional RNNs or neighbor. So GRU is essentially a bit simpler structure than LSTM, but it solves the problem of vanishing gradient and the long range dependency problem of the simple RNN. Here also, as we have discussed in LSTM, that this gated recurrent unit going to improve this architecture or a naive architecture by introducing the gating mechanism. So there is few gate. They introduced two gates here. This update gate and one is reset gate. That we will discuss here. So GRU improves this RNN by introducing the gating mechanism that controls how information flows through time. They are very similar kind of than what we have seen earlier in LSTM, but it's a bit simpler. Now, before going to discuss in detail, this is overall architecture of a single node of a GRU. As we have seen here, is it main two input, one from HT minus one from the state input from the previous state, and the current input, this XT. Okay, and there is a two gate, update gate and reset gate, and these two gate will going to decide which informations to be forgotten or removed and which information from the previous state is being taken into memory cell. Similarly, this kind of thing is also how this HT is going to be derived. Let's see. Now, this naive RNN mainly faces two problems that we have discussed. One is vanishing gradient problem, and vanishing gradient problem basically make the convergence very slow, almost for initial layer it stops, and by this reason it can't handle the long range dependency, and it is called long range dependency problem. Now this gated recurrent unit going to improve these problems of this neighbor by introducing this gating mechanism that controls how information flow through time. So they utilize two gates, as we said. One is update gate and a reset gate to manage the information flow, providing a simpler or faster training process and performs better to handle long range dependency in sequence modeling. So this is the basic understanding of this. That's the basic definition. Now, if we compare with a simple RNA with this, you can see here this is simple RNA that we have seen before. This is a very simple kind of thing. And here we introduce two gate, and how these two gate manage the information flow in this unit, that we are going to understand. Okay. Now, first we introduce the update gate. This is the update gate. So which this gate is going to do? This gate decide how much information from the previous sequence state HTML should be retained the next time step. So how much of HT is coming to this HT kind of thing, okay, or in output. So what is the ZT or ZT? This is sigmoid because it put a sigmoid and non-linearity here. Now this is weight matrix W of X because of XT, and U for update gate to XT plus W of H U to HT minus 1. So this is the update gate, and that is this ZT. Next is reset gate, that is RT. How RT is being formulated is very similar to this update gate, that Wx of R, only difference is this U, it is for update, R for reset, into xt this plus W of H, R for reset, WHT minus 1. So this is coming here, this is coming, this is coming here. So we get that. So these gates allow GRU to control the flow of the information in a more efficient manner compared to the simple RNA, which solely rely on the hidden state. So now we define this what is RT and what is ZT or ZT. Fine. Now to find out what is there is another called this candidate hidden state, HT tilde. So this is the potential new hidden state calculated based on the current input and the previous state. So it is what is the potential new hidden state. That means the new information based on this input and the previous state input. So it is Wx. This is coming from this plus RT. This RT is basically reset gate to WH HT. So this is H RT plus W, and in this summation we put a tan H non-linearity over this. So this is HT tilde. So what is this? This is the potential new hidden state calculated based on the current input and the previous state. Right? So this is this. Why it is candidate? It may or may not be the hidden state. It depends on this ZT. Now hidden state HT, how it is being calculated? The final hidden state is a weighted average of the previous hidden state. That is interesting. Weighted average of this state HT1 and the candidate hidden state HT are based on the update gate. Now here you can see 1 minus 0 of t. Now if ZT is 1, then this HT is 0. So there is no information is coming as part of just ht minus 1 is completely go to the ht. So that is very interesting. The final hidden state is a weighted average of the previous hidden state ht minus 1 and the candidate hidden state ht tilde based on the update get zt. So this z of t ht minus plus 1 minus z of t 2. So what we can understand, based on this zt zt, we decide the previous state will be in ht or this candidate state h by t will come this, or both partially come, that also possible, because if z is 0.5, that is kind of thing. So this is the main thing to understand. Okay, then ultimately when we get this ht, we can put w to ht, get fine, and put a softmax to get the output yt. Now here we can see that this zt is upgrade get, rt what we have discussed is set get, and h tilde is the new memory content, and ht is decided about this. The question is, in this formulation, how GRU solves the long list dependent? Now you see the previous example. Kid watching the cartoon channel, the TV, is very happy. Now this is set with this kid. If it is a singular, it is is. If it is a plural, it's are. Okay. So here you can see this. Now in between, if z is 1, so this ht is carry forward. Ht minus 1 is all these words. If zt we put 1, this ht, so it remembered for this particular contextual relation or this long range dependence. And in this way, this gating mechanism is going to help GRU to model this long range dependence. Now we are going to understand a sequence to sequence model using our RNN or LSTM framework. So LSTM or RNN have been used widely for processing and making sense of sequential data. Okay. And the usual approach, the encoder-decoder architecture for sequence to sequence task. So that is, sequence to sequence means what? There is a one language, let's say Hindi, main ek chhatra, and it is converted to the or translated to the English. I'm a student, like this. So here what we have discussed earlier, that this is the encoder-decoder architecture. This encoder is encoder RNN or LSTM, or it is a decoder. Now between this encoder, after encoder, whatever the output of the total encoder called context. That means the abstract of this sentence. And this is as the output from the last hidden state. It's called context, and this context is going to decoder. And in this decoder also very interesting architecture. In the first node, time instance 1, it is start. It is going to the first the word of the sentence. Then this word is coming as input to the second. and this will be then the second step. Then this second input is coming, the input to the third instant of time, and going to get the third instant target input. Then this output is again go to the input to the next state, and this and so on it is. So this is the sequence to sequence model normal architecture that we have to some extent explained earlier. Okay. Now, two basic things here important to understand. One is this context. What this context is going to play a role. At we can very simplistically that what is the meaning of the sentences. Not exactly meaning. So at least there is some you can say syntax or some contextual relations that is understood by this context vector, and that essential state input to this decoder. So apart from this, in these inputs, this state input is going to. Now what is required to make this kind of model very successful? That we have to understand. So the current node of the state has access to the information whole input seen so far. So that is very interesting here. That means when we are going to predict this, we have access not only to the encoder but to this, the previously generated input, output. So that is interesting to understand that the whole input seen so far, that means so what are the input is being given. From the encoder point of view, if we try to understand that the final state of encoder RNN or this RNN is a context, and this input should be known by these states of the decoder. But by virtue of this context vector, we want to understand what are the input to these encoders. So under these circumstances, this is the basic understanding of this. Thus only this context vector is come here. So there is some problem we can face. What problem? The neural network, because here this is basically a neural network, needs to able to compress all the necessary information of the source sentence into a fixed length vector. So this encoder, this is ultimately it is a neural net through in a time axis, and it essentially creates the context vector or produce the context vector. So this neural net should be good enough to understand that the individual input should be present or should be somehow incorporated in this context so that the decoder can take the problem. And this is a really complicated job, even for a very simple you can say the neural net for like this. So this is a bit complicated job. So essentially or most importantly, when this sentence is bigger, what do you mean by bigger sentence? Then the longer distance or long range dependence long range contextual dependency is very tough to handle by this kind of RNN. LSTM can handle, but still, if there is a bigger sentence, then what all these inputs, or at least the somewhat abstract important information of this input should conveyed in this context vector so that it conveyed to the decoder. So the tasks become much complicated if the sentence is that, and especially if this sentence are not present in a training corpus. At the testing time it will be real. So another problem is that this architecture lies in the fact that decoder need to represent the entire input sequence that मैं एक छात्र हूँ. So this is in a single vector C context. So it very much possible that it cause the information loss because this is a single vector and this is so much. If it is the longest sentence, is a sentence of 30 words, say, then it is very tough to find all the important information to be gathered in this single context vector. So there is a certain reason that this information, some information may be lost. In addition, this context should be deciphered by this decoder, because if it is the longest sentence, definitely this context become very abstract, and that should understand by this decoder, then only it will produce the problem. If they not understand the context, is a problem. So this approach essentially has this kind of problem. The major aspect is that only the output of the last node is coming as a context. That is the major issue here. Now, to solve this issue, a very interesting concept has been proposed that is called attention. So what do we mean by attention? Attention mechanism helps to look at all hidden states from the encoder sequence for making prediction, unlike vanilla encoder-decoder approach. Vanilla encoder-decoder approach, what we have discussed earlier. This is the vanilla encoder-decoder approach, and very straightforward and simple architecture. Now here we introduce attention. Where it is different, then you can see in this figure that is our previous model. We have drawn in different way. This is our encoder structure. This is E1, E2 up to ET. And this is X1, X2. And from the final state, this HT is a context. And this context is H0 of the decoder. And this decoder is another. So this is a one RNN, let's say for RNN, name for LSTM also. Is another RNN. Or is LSTM, another LSTM, something like that. So here it is the same architecture like this. Now we introduce attention. What is the major difference here? You see, in attention, how you compute attention, that rather than only coming from HT, the information is coming from every hidden layer or every state output of this H0, H1, H2, HT minus dot HT minus. And this attention is going to, for when we calculate it, for D1 it is coming here. This is actually our context or attention, whatever. It is coming here, it is coming here, it is coming here, and so on. So the basic understanding is that attention is what? Attention is basically that is going to calculate it. Attention is being calculated by taking input from every hidden outputs, that or every state. So definitely this formulation has much wide information than this, because here in this all this calculation done and from the last state we take the output as a context, but here all this information is gathered. So what do you mean by attention? Attention is a mechanism that allows a neural net to focus on the most important parts of the input when making the prediction. So instead of treating all the input information equally, attention assigns different weights to different parts. Definitely, if we analyze a sentence, then some of the words have more important than other words. Or if we reading a text, some portion of the text or some sentence is very important, rather all the sentence. So attention is basically try to do this, try to find out the most important part of the input, rather taking all consideration. Okay. So what traditional neural networks do? Compress all information into a fixed size vector. That's what we have seen here, that it is basically all the information is somewhat kind of averaged or kind of taken care of. But in attention, to try to find out some weightage over the inputs or different parts of the inputs. So by these characteristics that compress all information in a fixed size vector, it's a context vector, we may lose some information. Some important details we can lose, and especially for longer sequences or sentences. So attention is what is doing? It dynamically select the relevant information to improve the performance. Basically, when we analyzing a sentence, some part is more important, some is not that much important. So attention find out the important part and put more emphasis on this. It also improve the interpretability, because now we can see what the model is focused on. Okay. So attention is very important. Now when we are put attention in sequence to sequence model, we have seen that in our previous this diagram, what attention is going to do, that it basically provide a mechanism that allows decoder to focus a specific part of the input sequence, rather generating the entire input sequence. So here what will be the first case where attention is not there. All this is somewhat abstract, and this particular context seen by decoder. Rather, here what we put in this way, that we can put from here, from this h1, h2, 2 dot dot ht1, and not only that, we put some here some learnable parameters. I will see later, so that we can selectively choose the inputs or different parts of the inputs. If it's a sentence, some word is important, some others, that we can choose. That essentially we can see. So I write this, I read this sentence again. Attention is a mechanism that allows decoder to focus on specific parts while generating each output, instead of relying on the singular fixed context. So what without attention this basic sequence to do? This encoder processing the input sequence, and it compresses the entire sequence in a single context vector, and decoder use this vector to generate the output sequence that we have discussed. And the problem, definitely we compressing some information, okay, so that maybe we can lose some information. Definitely it's a poor performance of longer sentences, because if sentence is longer, it is very tough to compress all the information in a single context vector, and a difficulty in capturing longness dependency. Okay, so this is this. And how attention solves this? Instead of using only a final encoded state, it's all encoder hidden states that we have seen here. All encoder hidden state are taken, okay, and each decoding state compute a score between the decoder state and each encoder state, and this convert this score into attention weight as well. So computes a weighted sum of the encoder states and use this as a dynamic context vector. Now this is very important. Now this attention weight, by virtue of this, these are learnable weights, and this virtue of this weight, now you can see if this is a particular for a sentence, you just consider which word is most important. Definitely how attention solves this. Attention word is definitely much. Now if we can say that all put emphasis all this word equally, or we put the attention word more emphasis, definitely we should do this, put more emphasis on attention. Okay, the same thing. So there's the concept of scoring, and this score we will see later based on this attention weight, that this score essentially convert this score into attention weight by this operator and compute the weighted sum to the encoded states and use this as a dynamic. So this allows the decoder to look at relevant input words, which input words important, like this, when generating each output word. So that essentially important. Now see how we take an example and try to understand how this has been done. Now here it is the example. Now how to compute attention in this context vector. So the question that what we said that we put emphasis on some word, but how? how does it decide which states are more or less useful for every prediction at every time state of the decoder? That is the major question that I am going to answer. So we put some neural net for that. So this is a neural net that learn which hidden encoder states to attend and by how much. So for that reason, what will find? We first compute the alignment by this net. That input to this neural net, this F attention is this ST minus on the previous state, this, and HI. This HI is basically this particular in the state, this HI, this thing. Then we normalize this ETI thing, that use the softmax, we get alpha T of I here. Now the context factor is computed as linear combination of this. Then we can put a linear combination and find this. By this we context factor. We take the only 4 states, that is good. That alpha of Tk to Hk, and it sum it up to K1 to T. Capital. Now this context vector used in the decoder. Now as you see, this context vector coming to the decoder. This is overall diagram. We come iteration by iteration so that the picture will be more clear. Okay. Now start with first iteration. In first iteration, what is the for assumption? The RNN, LSTM or whatever is the 4th state. So we have seen is 4th state and is taken as the both encoder and decoder. So encoder and this decoder. In the first iteration for this decoder, so S0 is coming, H1, H2, H3, H4. So H1, H2, H3, H4. These are the state, hidden state from input of F attention. So F attention, this HI is equal to 1 to 4 and S0, only S0 is available. And it computes what? This alpha I1. So alpha 1, 1, alpha 1, 2, alpha 1, 3, alpha 1, 4. So this alpha I is equal to 1. So the softmax of this E of I, E of 1I. Now the context vector C1, how it is generated? It is K to 1 to 4, this T is equal to 4, alpha 1 and 1 comma K, so this is 1 1, this and HK. So it is alpha 1 1 to H1, alpha 1 2 to 2, alpha 1 3 to H3 and alpha 1 to H4. And the context vector, how it is? This is Y0 here. So just completeness we write Y0, there is no Y0, S0 and C1 for the first 0. Okay, come to the next iteration. Next iteration also same thing. For example, this is a 4th state, this, and now this input to this is S1. Now S1 is coming to the input of this F attention and for these states. Okay. Now we can find normalize this score at alpha 2I, the softmax is 2I. We can get C2 of this. This is the similar thing. We can get C2 here for 2K and HK. And now this context vector is S2. Enter is useful decoder. So C2 is coming here. Y1 is coming here. So Y the input output of the first state come to the input to the second state. And Y1, S1 and C2. This is the input to this decoder. And this in iteration by iteration. In third iteration, almost similar thing is going to do that E3I. So what is the input to this F attention? Is S2. Now this is from S2 is coming, from S2 is coming, and this H1, H2, H3, H4, and alpha 3i and C3 is obtained. So alpha 3i, 3, 1, 3, 2, 3, 3, 3, 4, this, and C3 by linear combination we can get C3 by this, and we can get this S3 out of this S3. Okay. So decoder Y2S2, and finally we get iteration 4. So there you can say S3 and H1, H2, H3, H4, put this, and the similar fashion, and so on if it is. So by this way the attention is okay. So in summary, in this lecture we have discussed the gated recurrent unit, that's here. Then we briefly discuss the GRU architecture. Then a sequence to sequence modeling discuss with respect to RNA LSTM. Then we find what is the context vector, what is the problem of simple context vector, and we introduce attention and how attention solves this problem, and then how to compute attention through RNA. This next topic we start here.